In this video, we will explore the geometrical relationships between two planes. Two planes can only interact with two possible outcomes. Either they intersect at infinite number of points, or they don't intersect. If two planes intersect at infinite points, there are two possible cases. Firstly, they are non-parallel and thus they intersect at a line. For example, something like this. I have the first plane here and the second plane somewhere over here, such that they will just intersect along this line. Secondly, they can also be the same plane, thus they will intersect at a plane. So they are essentially the same plane like this and like this. Thus they will intersect at infinite number of points as well. And if they don't intersect, there is only one possibility. The two planes must be parallel to one another. We can make use of the GC to determine how two planes intersect. But first, we have to convert the equations of the planes into Cartesian form. After conversion, we can see that they form a system of two linear equations with three unknowns. And thus, we can make use of the simultaneous equation solver from our GC to solve this system of linear equations. As with the intersection of two lines, we will need to know how to interpret the results shown by the GC. The first type of result that the GC can show us looks like this. x1 and x2, which are x and y, are functions of x3, which is z, and x3 is equal to x3. This result represents intersection at a line, and we will need to know how to convert this answer into the equation of a line. We can rewrite these three equations as x equals to 3 plus 1z, y equals to half minus 2z, and z equals to 0 plus 1z. And now I can group them up like this and let z equals to lambda. And therefore, I can say that the solution can be written as r equals to 3 half 0 plus lambda multiplied by 1 minus 2, 1, where lambda is a real number. Next, we can have a solution screen that looks like this, where x1 is dependent on both x2 and x3. This represents intersection at a plane, or that the two planes are actually the same plane. And finally, we can also have no solution, meaning that the planes are parallel to each other but not the same plane. Putting both equations into the GC, we can solve for this set of simultaneous equations, which gives us x equals to 1 minus 4 over 5z, y equals to 0 minus 1 over 5z, and z equals to z. So 0 plus 1z. And therefore, they will intersect at a line, and the line is r equals to 1, 0, 0 plus lambda minus 4 minus 1, 5. Lambda is a real number. From the GC, we get a solution of x equals to 1 minus y minus z, y equals to y, and z equals to z. Therefore, we know that pi 1 and pi 2 are the same plane. Now, solving using GC again, we see that there are no solutions. And therefore, what this means is pi 1 and pi 2 are parallel and they are not the same plane. Formula. To find the angle between planes pi 1 and pi 2, we simply have to use the formula directly. So theta equals to cos inverse of n1, n2 over mod n1 mod n2, which is 1, 1, 1 dot with 2 minus 1, 1 divided by mod of 1, 1, 1 and mod of 2 minus 1, 1. And this, after simplifying, becomes cos inverse of 2 over square root 3 square root 14. And if we press our calculator, this becomes 72.02 degrees, or we should round off to 72.0 degrees, correct to one decimal place. To determine the distance between two parallel planes, we can make use of the formula for the distance between the origin and a plane. Recall that if I have a plane, let's say its equation is r dot n equals to k1, its distance to the origin O will be k1 over mod n. If now I introduce a second plane over here, such that it is r dot n equals to k2, its distance to the origin will be k2 over mod n. Therefore, the distance between the two planes should be just the difference between their respective distances with the origin. And thus, we can say that the distance between two parallel planes is this: k1 over mod n minus k2 over mod n, and we put a big pair of modulus outside to make sure it is positive. Note that this formula works when k1 and k2 are of opposite signs as well, and we do not have to specially change any of their signs. For example, if we have r dot n equals to 1, and we have the plane r dot n equals to minus 2, we know that their distances to the origin will be 1 and 2, but they will be on opposite sides of the origin, and this distance is 1 over mod n, this distance is 2 over mod n, and therefore we can rewrite this as 1 over mod n minus negative 2 over mod n, which gives us 3 over mod n, which is still the same as the given formula. In example 3, we are going to find the shortest distance between two planes. But now we see that the coefficients of the two planes are different, but we should realize that they are still parallel to one another, because I can rewrite pi 2 as x plus y plus z equals to 5 over 2. And therefore, the shortest distance between the two planes will be mod of 5 over 2 divided by mod n, which is mod of 1, 1, 1, minus 1 over the same modulus 1, 1, 1. And this gives me 3 over 2 over square root 3, which becomes half square root 3 units.